Hi, in this module I'm going to introduce the forward-backward algorithm for performing exact and efficient inference in hidden Markov models, which are an important special case of Bayesian networks. So let's revisit our object tracking example now through the lens of hidden Markov models. So recall that at each time I, there's an object that is at a particular position hi. The object might have gone this trajectory. And at each position, there's also a noisy observation, 0, 2, and 2. So let's formally define a probabilistic story for how these data might occur. So we start at h1, which is the position of object at time step 1, and we're going to generate this position uniformly at random, probably 1/3, 1/3, 1/3, for each of these possible positions, 0, 1, or 2. And then I'm going to transition into the second time step. So in general, I'm going to look at hi minus 1, looking to hi, which is going to be up with probability 1/4, the same with probability 1/2, and down with probability 1/2. So mathematically, this looks like this. Hi can be hi minus 1, minus 1, the same or plus 1 probabilities. So this transition distribution is also used to generate h3 given h2. Now, at each time step, I have an emission of E1, E2, and E3. And in general, I'm looking at the actual position at time step I, and I'm going to generate EI according to essentially the same process, which is up with probability 1/4, same with probability 1/2, and down with probability 1/2. And this is local conditional distribution formally stated. So now I multiply all the local conditional distributions together. We have the probability of start, h1. We have the probability of hi given hi minus 1 for each subsequent time step, times the probability of the noisy sensor reading ei given the actual position hi for all the time steps. And this gives us the joint distribution over all the actual positions and sensor readings. So now let's ask questions about our hidden Markov model. So there's two types of questions which are common. One is called filtering, and the other is called smoothing. So the filtering question is something like this, which is I'm interested in a particular object location at a particular time step, h2, given some evidence, which is all the sensor readings that I've seen before that. Smoothing is similar, except for I, in addition, condition on the future. So my observed E3 is equals to 2 as well. So notice that filtering is actually a special case of smoothing if we marginalize unobserved leaves. So to show this, suppose we have just this Bayesian network or HMM, and I didn't observe E3. If I didn't observe E3, E3 is just unobserved leaf, and I can marginalize it out by just removing it. Now H3 is unobserved leaf, and I can remove that as well. So now this filtering query is actually a smoothing query where there is no future because I don't observe the future. So now let us just focus on smoothing queries without loss of generality. So the forward-backward algorithm is based on dynamic programming, and the key idea is to represent the set of all assignments using a lattice. So this lattice is a directly acyclic graph, not to be confused with actual HMM or Bayesian network. There's a start state and an end state, and each column is going to represent a particular value, and each row is going to correspond to a particular variable. So, and each path through this lattice now is going to correspond to an assignment of values to all the variables. For example, if I go through this path and set h1 equals 0, h2 equals 2, and h3 equals 1. So this is just a very compact way of representing all exponentially many assignments in a polynomial-sized object. So now I'm going to attach weights to the edges. So edge start to any of these initial states has weight, the start probability times the first emission probability. For example, this edge here has weight probability of h1 equals 0 times probability of e1 equals 0 given h1. Because e1, remember, was observed to be 0. So I've plugged in that evidence. So now the subsequent edges are between some hi minus 1 and some hi. And that has weight the transition probability times the emission probability of the destination state. For example, this edge here has weight probability of h2 equals 0 given h1 equals 0, that's the transition, times probability of e2 equals 2, which is what we observe as evidence, conditioned on h2 equals 0. And this one is h3 equals 0 given h2 equals 0 times the emission probability. And this edge doesn't have anything on it, so we'll assume it to be 1. And now, each path, as we stated before, from start to end, is an assignment of all the variables, but in particular, it has weight that's equal to the product of the edge weights. So this path here has weight, which is simply the product of all these purple numbers. Okay, so, and that weight is actually the joint probability of this particular assignment and the evidence. Okay, so now the key part is that smoothing queries, such as probability of hi given e equals e, is simply the weighted fraction of paths through hi equals hi. So for example, if I'm interested in what is the probability of h2 equals 1 condition on evidence, what I'm really asking in the context of this lattice is what is the fraction of paths that pass through this node compared to all paths. So stated differently, I'm going to look at all the paths through this node, add up all their weights, and divide by the sum of the weights over all paths. So this gives us a really nice graphical interpretation of these smoothing queries. So now we can compute those quantities using a recurrence. I'm going to define two types of objects, forward messages and backward messages. Here's our lattice. So the forward message for each node here is going to be f of I written of h of I. And this is supposed to be the sum of weights of paths from the start to a particular hi equals hi. So for example, f2 of 1 is going to be the sum of the weights of all paths from start to h2 equals 1. And I can compute this recursively as follows. So all paths that go from here to here have to have a previous position, which is one of these. So I'm going to sum over all possible hi minus 1, so values of the previous variable. And then I'm going to recurse on fi minus 1 of hi minus 1, so the sum over all the weights to each of these previous locations, times the weight of along the edge from a particular hi minus 1 to hi. So the backward message is analogous. So bi of hi is going to be the sum of weights of all paths from a particular hi equals hi to the end. So b2 of 1 is the sum of all paths from this to the end. And this, again, is recursively defined as looking at all next nodes, so hi plus 1, and recurse on b of I plus 1 of hi plus 1 times the weight of the edge from between the hi and hi plus 1. Okay, so now having defined forward and backward messages, I can multiply them together to form Si, and my claim is that the sum of the weights of all paths from start to end that go through a particular node is exactly Si of hi. Okay, so for example, if I'm looking at this node again, Fi is looking at all the ways to go from start to this node, and then the Bi is looking at all the ways to go from this node to the end. And if I multiply all those two quantities together, then I get all the paths from start that go through this node to the end. So now we're almost done. We can take these SIs and then we normalize them over all possible other values that hi could take. And that gives us exactly the probability of hi equals hi given the evidence. And this is exactly the smoothing quantity that we're looking for. What is the probability of H2 equals 1 condition on evidence? Now, putting things together, the forward-backward algorithm is going to simply compute all the forward messages proceeding from 1 to 2 to 3 all the way up to n, where fi depends on fi minus 1, so I'm going forward. And then it's going to compute all the backward messages going from n down to 1 because bi depends on bi plus 1. Now I'm going to multiply everything to the fi and the bi together to compute si and normalize, and that gives me the answer to the smoothing question. So the runtime of this algorithm is, so we have n time steps, and for each of the time steps, I have number of domain elements that I need to consider. So this is the number of nodes in this lattice. And I have also another multiplicative factor of domain because to compute the recurrence. And this is exactly actually the number of edges in this lattice. So one other note is that notice that the forward-backward algorithm actually computes all the smoothing queries for each I. And this takes time. The time complexity for computing all of them is exactly the same as computing the one for any individual one. And that's because there's a lot of shared computation. So the forward message here that's computed is used down here, and same with the backward messages in the other direction. So let's look at a quick demo of this in action. So here is the object tracking HMM. So we have H1, H2, H3, and we have the various probabilities of H1, 1 given H1, H2 given H1, E2, H3, and so on. And now I'm interested in the probability of H2. So here, notice that I'm actually not going to run forward backward, but I'm going to run this more general algorithm called sum variable elimination. So the details are going to be a little bit different, so don't worry about it too much, but I just want to give you a flavor of how it works. So here, the first thing I do is I compute this factor, which is actually the forward message where I've summed out the previous time step, H1. And then I'm going to compute another factor, which is summing out the backward message, which sums out H3. And then I'm going to multiply them together, and I get the probability of H2 to be 0.61 and 0.3. All right, so to summarize, we've presented the forward-backward algorithm for probabilistic inference in HMMs, in particular answering smoothing questions. So the key idea behind the forward-backward algorithm is this lattice representations, which allows us to compactly represent paths as assignments and the weights of each assignment to be the product of the edge weights. That allows us to define a dynamic program which computes the forward and backward messages in an efficient way. And now, if you multiply the forward and backward messages and normalize, now you can compute all the smoothing queries you want in the same amount of time as computing any one of them, because there's a lot of shared computation. All right, that's the end.